Yeah, good afternoon and welcome back to the last talk of the day. And it is my pleasure to introduce Professor Raphaël Danchin from Paris-Est Cathay University, which is known as Paris 12. And he finished his PhD in 1996 from École Polytechnique. He was a CNRS researcher at the Paris 6 till 2002, and since 2002 he is a professor at Paris 12. And in this workshop, he's going to talk about partially dissipative hyperbolic systems.
Okay, so thank you very much for invitation and for presentation. So, well, this series of talks will be a bit different from the ones that you had so far. There will be some relationship with fluid mechanics, but maybe not so obvious. It will be, I mean, well, it's somehow more general. However, the main examples that I will give will come from fluid mechanics. So the initial motivation comes from, so I can write until here maybe. So you see, you consider general systems of conservation laws. So of this type, for example, okay, I'll write something a bit general. So, okay, so if one notation is not clear, let me know. So here, this is actually a system. I mean that the functions f0 to fj are given. They are defined on some phase space, which is an open subset of Rn. So the unknown u depends on the time and space variable. So, and we want to consider this kind of system in a time interval cross Rd. Okay, so there is no boundary, and the situation with boundary will be quite different and certainly much more complicated. So these kind of systems have been studied for a long time because they come into play in many modelizations of fluid mechanics, for example, or traffic flow or whatever. Whenever you have some quantity which are conserved, so it's well known. Well, the basic result, the scalar case in dimension 1 is well understood. Well understood, I mean, you know how to construct global solutions, you know how to get unique solution under some conditions, in a rather general framework. It's all results by Glim and Khrushchev. Of course, there are more recent results, but the first one, this run by Glim and Khrushchev in the 60s. But the situation when you have either a system or even worse when it's multidimensional, it's much more complicated. In general, so you have a good local so of course there are some assumptions that I don't want to give now, but under some assumptions on these functions, you can get local well-posedness in Sobodé spaces whenever the Sobodé space is embedded in the set of Lipschitz functions. And this condition is very important. So if you are in dimension D, this is equivalent to S greater than D over 2 plus 1. Okay, so the meaning LWP is local well-posedness, which means that for given data, you have a unique solution for small time. But in general, you have finite time blowup, even for small data. Of course, you can produce examples where it doesn't happen, but in general, it's what you have. You have finite time blowup. Atypically, the type of blowup that you have are shocks. So, however, in the applications, if you think of fluid mechanics, for example, an example of fluid mechanics, well, the simplest one, in fact, it's a toy model for fluid mechanics, is Burger's equation. Okay, that you may write in that way if you like. So for this one, you have finite time blow-up. And then, so I will not talk much about Burgers because this situation is well understood, but much more interesting model is gas dynamics. So the simplest one is a Euler equation, but not the incompressible one, the compressible one. So there are two unknowns, which are the density and the velocity u. And the equation may be written in that way. So you also, formally it looks a bit like the incompressible Euler equation, except that you have the two unknowns, which are the density, rho, which is non-negative, obviously, and the velocity, which is u. So it's an example, if you are in dimension d, it's an example of a system of conservation laws with d plus 1 equations in dimension d. And then the phase space, well, it's given by this condition. So you have to be careful because here the pressure term is given. I mean, it's a given function. The pressure. It's not a Lagrange multiplier associated to divergence-free condition. There is no divergence-free. The pressure is given. Sorry? Well, so far I put it very general. I mean, yes, you are right. A popular pressure is rho to the gamma, something like that. But I stay very general for the moment. Of course, if you want to, that it enters in the theory of system for which you have local well-posedness, then typically you have to assume that the pressure is an increasing function. Maybe not everywhere, but at least in the neighborhood where the reference density that you want to consider. Okay, so however, in the application, if you think of gas dynamics, in general, you can also take into consideration some friction terms, at least in this equation, of some viscosity terms. So some class of system which is maybe more interesting for the applications is to add, so you keep the first two terms, but you add some friction and some diffusion terms. So typically, you may look at more general systems. Well, more general, I mean, of this type. So maybe I will use a short notation here, so that I don't want to have sums everywhere. So I will denote this by divergence of Fu. So with this short notation, this second term is like this. And then I add some friction term. And on the right-hand side, I put some viscosity term, or well, whatever, which is of this type. And I assume, so it doesn't mean anything because I did not, so far I didn't have any assumption on F0, but assume that here you just have U. So in that case, I want to have some positivity. So this term is a friction term. It has to be positive, at least non-negative in some sense. I will specify later on. And this one you may see this second order term as a diffusion term, and also it will have some positivity, non-negativity, in the elliptic meaning. Okay, I am still very general. But typically, if you think of the gas dynamics, you may have such terms, but not on the density equation, because the density equation corresponds to the mass conservation. So you don't expect to have friction terms here or diffusion. But you may have in the momentum balance. Okay, what I mean here is that these two terms in the application, they are not necessarily positive. They are just non-negative. Okay, so what happens, the question is, that we want to address is, what do we have to suppose to get global existence So I cannot ask too much. I mean, I don't expect to have global existence for any data, but global existence, or I am interested by unique solutions. So let's call it strong. By strong, I mean that I also have uniqueness, well-posedness result. So maybe not for all data, but at least for small data. And what I mean by small data, it's maybe not small in absolute meaning, but it's a perturbation of some constant solution, typically. Okay, so there is an easy case. The easy case, well, easy, I mean, you may have some technicalities, but in general, you will get the result. It's if you have a strict positivity of N or B. What I mean that if you consider viscous Burger's equation, well, it's well known that you have global existence even for large data, but it's kind of miracle. It's not the general situation, and for the damped, you have global well-posedness, and you also have it for the damped Burgers. By damped Burgers, I mean that where is it? Here I put a plus U, for example. Then you have global existence for small data. But this is not the most interesting situation, I said before, because in general, in physics, you have at least you have some quantities which are conserved. So the situation that is more interesting is that the one, if you come back to gas dynamics, is the one where here you add some viscosity or friction term. So let me go back to gas dynamics. So you still have the first equation. I don't change it. And for the second equation, so for example, you can put either a friction term, so typically kappa OU, or a viscosity term. So as it is a system, the viscosity here is a bit complicated. I mean, it doesn't need to be just a Laplace operator. Something that is a bit more involved is something like this. So you have two parts. So there is one part with the symmetric part of the gradient, and another one which is correspond to the, well, it's called the bulk viscosity. So where you have this term. And still you have the pressure. Okay, so what happens if you add in the left-hand side? So you have some condition on the coefficient here. So you assume that kappa is positive. Okay, so this is a friction term. And for the viscosity coefficient, you assume that mu is positive, and the sum. So you have the second condition ensure that here you have some elliptic operator, and you have this. Okay, so this is a condition that you need to have positivity of the operators which are here. Okay, so and you assume an addition. So now you have to make some assumption on P. So you assume that P prime is strictly positive, for example. So in this situation, it has been proved by, I'm going to give an history now, for example. So it is known that in these two situations, you have global in time situation solutions if you do for small perturbation. So you have global well-posedness for initial data, which are close to, for example, well, some reference density, which is a positive constant, and velocity 0. So let me do a short history of that. So first for some short history. So the theory of well-posedness for general system of conservation laws, or at least a subclass of it, which is called symmetric or symmetric hyperbolic system. So has been done by Cato, Kreis, and so on in the 70s. But the situation I am interested in, for example, the compressible Navier-Stokes equation. I should give a name to my system. The second case, it's the compressible Navier-Stokes equation. And the first one, let's call it the damped Euler equation. Okay, for the compressible Navier-Stokes equation, it has been done by Matsumura and Nishida in the early 80s. But the first work that addressed systematically the question that I put here, what kind of condition you need to have a global well-posedness for small data. It's in the PhD of Kawashima. In 86. So in his PhD, Kawashima he considered general system of this type. He did some quite general assumptions. So first, the white part has to be solvable without the other ones. So it has to satisfy the conditions which have been discovered by Cato and Kreis, for example. But then it's not enough. You need also to have some compatibility conditions with the other two terms. And to get global well-posedness, he found out a sufficient condition, which is called now Shizuta-Kawashima condition, to get global well-posedness for small data. Okay, so it looks that the question has been completely solved. Not quite, because this is a quite high regularity framework. And I will explain in a moment what I want to do. And then after Kawashima, there was much more recently, there was an interesting paper by Bochard and Zoisois, where, so it's about 2010, I think. They consider a special case of Kawashima, the case where there is just friction terms. And they proposed a new approach that allows to prove global well-posedness in situations which were not covered by Kawashima, because the condition that was found by Kawashima was just a sufficient condition. Okay. So all this was a high regularity framework. It was so Waddell spaces with high indices. I don't remember exactly, maybe this or even more. I don't remember. Probably this is the condition that they have. So what is my goal? So the goal of the talk, or the lectures, is to somehow give a new approach of the study of these systems. So don't worry, I will not do it on the general, well, the method works in a quite general framework, but I will mainly concentrate on this system of gas dynamics, okay, which is already interesting. So the goal is to do it, is to find necessary, well, sufficient conditions for global well-posedness for small data. With, so I will not explain what it means today, but maybe not even tomorrow, but probably after tomorrow. So with critical regularity. So it may be, in general, when you talk, when the terminology critical regularity is employed when you have systems which have some scaling invariance. So if you look at this, at the degree of generality, clearly it's not the case, because here we have very complicated nonlinearity. Here you have two types of zero-order terms and so on. So there is no really scaling. But even if there is no scaling, it's not too difficult to find level of regularity below which you cannot expect to have well-posedness at all. Okay. So, and what is why do I want to do that? There are several motivations. Well, there is a first motivation that can seem a bit surprising, that when you have a critical level of regularity, you have no freedom. So it's in sharp contrast with the talks on, on constructing infinitely many solutions for Euler equations, for example, because then you have somehow too much freedom. You don't know what kind of solutions you are going to construct. Here, once you adopt some critical regularity scaling, at least in the inequality that you want to prove, you don't really have freedom. Either they are true or they are false. Okay. And also, well, this is just for a joke, but more interesting, when you have critical regularity, you have, well, somehow you have stability of estimates by rescaling. And this allows you to look to study long time asymptotics. And more generally, various asymptotics. What I want to say is that you can put some parameters. Okay, for example, the friction term you can put some coefficient that tends to infinity and look at what happens. Here you can put some viscosity and make it tend to infinity. Look what happens. Okay, and then just by just some suitable rescaling, it will be enough to treat the case where there is coefficient 1. And thanks to that, you will get uniform estimates that will allow you to study some asymptotics. So like high relaxation or diffusion limit. Okay, so now I think it's time to give the plan of the talk. So today, what I will do today and tomorrow, and I hope I will finish tomorrow. I have to finish tomorrow anyway. So the first part will be linear analysis. So from a technical viewpoint and conceptual viewpoint, it will be completely elementary, in particular because I will do it on very simple systems. Anyway, it will take 2 lectures. And then after that, I should be able to look. So well, for simplicity, I will not look at the situation when you have the 2 terms together, okay? Either you have this one or this one. But if you understand the 2 situations, it's not too difficult to do mixtures. Okay, so I will look at the partially dissipative situation. So partially dissipative systems means that you have n, but not a b. And in this part, it will base mostly on the PhD of my former PhD student, Krimbara. And plus a survey paper that was being published in the European Mathematical Society about maybe 2 years ago. 2 or 1 year ago, I don't know, yeah. And then, well, I will spend time on that, and maybe, I'm not completely sure, because that I will time, but if I have time, I will next look at a partially diffusive system. But you will see already on the linear analysis that there is much similarity between the 2 situations. And so this part is based on a PhD by Adogbo, well, which is not yet finished. Okay. So do you have any questions? No, it can be any dimension. Yeah, something important that, well, most of the case would be any dimension, but you have to think, not today, but for the non-linear systems, what I say is interesting if you are in a multi-dimensional case. If you are in dimension 1, you have much powerful techniques that give you much more results. So you have to think that, yeah, it's multi-dimensional analysis. So for today, it's the exact opposite, because for simplicity, I will concentrate on a 1D toy model. Okay. Okay, so let me start with the linear analysis. And with the study of a toy model. So the toy model is taken from gas dynamics. Okay, maybe I should write completely the first equation so that you understand what I mean. So imagine that I am interested by some perturbation of a constant density state. Okay, for example, so what I am going to do, what is the linearization of the first equation? So I set rho equal rho bar plus q, and the equation that you get is dq plus, so here you will approximate rho by a constant. So here you will have some constant that I call A. And well, it suffices to study the case where they are not right-hand side, because it's a linear system with constant coefficients, then you can use the variation formula to get the general situation. So for the second equation, what happens? So at least for smooth solutions, what you can do by playing with the chain rule and using the first equation is to put the rho outside, and then this becomes just convection term, u grad u. So once you divide everything by rho, and you linearize, you get this system, so DTU. So I assume that, so here it's, okay, I linearize the pressure term. It will give a term of the type B gradient of Q. And now for the viscosity terms, either if you are in the first case, you will just have U. And if you are in the second case, you will have something which is like Laplace of U plus, well, times some coefficient, plus lambda times gradient of divergence of U. Okay, for simplicity, it's just a toy model. I put the second coefficient to be 0. Or in fact, well, I manage that all this is just a Laplace operator. Otherwise, it doesn't change the behavior of the system, but the analysis is slightly more complicated. And I want to study the two situations together. So it's convenient here to put a fractional Laplace operator. So that I have the two situations together. And of course, so here, A, B, kappa are a constant number. I will make assumptions in a moment, but just assume for as a start that they are constant. What else? So here is a fractional Laplace. So B equals 0 correspond to Euler. And beta equal 2 correspond to Navier-Stokes. Ah, yeah, sure. So this one is Navier-Stokes. Okay, and as I want to have something very simple, I just sorry? No, the power here. I mean, well, it's identity operator. Well, it's a bit strange way of. No, but you will see that I want to do the analysis even for fractional Laplace operator because you will see that, well, it's the same. I mean, there is no change. You can, in the same stroke, you can treat any situation. So for simplicity, I assume that I am in dimension 1, but you can do the same in any dimension as an exercise if you like. So D1 for simplicity. And then it's very easy to solve the system explicitly in Fourier space. So you apply Fourier transform. So it transforms a function of x into a function of psi. And you apply the Fourier transform on this system, and what you get is this u hat plus, so this is the reason why it's convenient to be in dimension 1, because here you have a 2 by 2 matrix, which has explicit coefficients, so I xi. This one is I xi, and this one is kappa psi to the beta. And from this, it's possible to compute the situation. The solution is not what I want to do. What I want to do is just to understand the behavior by looking at the eigenvalues of the matrix, which is here. So, in order to compute the eigenvalues of the matrix, you need to compute the characteristic polynomial, which is x squared minus kappa x psi beta x plus a b psi square. And immediately, well, it's an exercise on the polynomial of the degree 2. As all the coefficients here are real, the stability condition necessary and sufficient stability condition is that these two coefficients are non-negative, or even positive if you want strong stability. What I mean by strong stability that I don't want to have exponential growth, okay? So necessary and sufficient stability condition is strong stability condition is kappa. So the friction coefficient is positive, it's not a surprise. And the product of these two numbers is also positive. Okay, so as you see, as you know, in fact, if you come back from here, B corresponds to the derivative of the pressure as a reference density, which means that you have to be in a neighborhood where the pressure is strictly the positive derivative to have strong stability. Also, it's not a surprise. Okay, so as I don't like to do computations, I'm very lazy, you can check that by rescaling. I mean, rescaling, you do a time and space rescaling. It suffices to look at the situation R equal B equal 1. And even more, and you can also manage to have kappa equal 1, except if beta equal 1, because in that case, well, you have all operators of the same order, you cannot expect to change everything, okay? But the situation beta equal 1 is not, it's a bit strange, intermediate situation, it's not really the one that I want to look at. The situation that I want really to study are 0 or 2. Okay, so what happens in this case? So maybe the best solution is to give some summary. Yeah, I can write here. I will draw a table to explain what happens. So, well, from this you can compute all the eigen. I can start the computation. So the eigenvalues are depends on psi, and they are of this type. So there will be kappa psi beta plus or minus the discriminant of this polynomial. Okay, I said that, well, okay, I can leave the general case, but anyway. So the discriminant is kappa square psi to beta minus 4 RB psi square. So you see that in general, depending on whether psi is large or small, it may be positive or negative. So there will be, in general, there will be a regime. It depends, it can be for large, it depends if beta is greater or smaller than 1. But there will be a regime with only real eigenvalues, which are positive, always positive, and a regime where they are complex conjugated. So it's what I want to summarize in this table. So low frequencies, high frequencies. So here you have beta smaller than 1. The intermediate situation where beta equals 1, and finally beta greater than 1. Okay, so what happens for low frequencies? If beta is smaller than 1, maybe I should look at my tables, it will be faster. So what I want to write is not the exact value of this. There will be square root on this. But the behavior when psi tends, in low frequencies, when psi tends to 0, you tend to have two eigenvalues, which are these two ones. Okay, which means that in low frequencies, you have two quite different behavior, which correspond to a fractional Laplace with power beta over 2 and 1 minus beta over 2. And for high frequencies, you have two complex conjugated eigenvalues that tend to be equal to this one for very, very large psi. So in the intermediate situation, you have only one regime. And then you can compute it if you like. It may be, so the regime, it depends on the value of kappa and d. It might be real or complex, depends. So here it may be an imaginary number, depends if it's negative or positive. And finally, in this situation, it's like here, but the behavior of low and high frequencies is exactly exchanged. So you have this in that case. Okay, so this table is very informative because if you look at the two cases that correspond to Euler and Navier-Stokes, beta equals 0 and beta equals 2, then here you will get 1, for example, here, 1 and psi square. So 1 corresponds to damped mode, so exponential decay, and psi square corresponds to the heat equation. And if you look back now at beta equals 2, we have this behavior, but for high frequencies. Okay, so it means that somehow there is a strong link between the case where you put a full Laplace or just damping. At the linear level, it amounts to changing low into high frequencies. Okay, there is something else that may be useful, but I will not exploit it today. Is that here, in this regime, it's real, and here also, which means that you have no oscillations in low frequency here and here. And if you have no oscillations, you can expect to be able to prove results, not only in an L2 type framework, but also in LP type framework. But now, if you are in the other regimes, you have oscillations, time oscillations. I mean that if you compute the situation, that you will have cosine and sine and so on, okay, due to this imaginary part. So we have to keep in mind this table if we want to go further in the analysis of nonlinear systems. Okay, something very simple, but that has to be kept in mind. So now, if my goal is to do the same for the general systems I showed before, well, I don't expect to be able to compute everything explicitly. So I need a method that allows to get somehow the same, to pinpoint the same behavior without doing explicit computations. Okay, so it's what I'm going to present again on this toy model. And what I claim is that at least you, just by using energy arguments, you can already have some quite good information. You will not get the whole table, but at least you will get a part of it. What you will not see, you will not be able to see the imaginary part, for example, but you will be able to see the rest of it. So let me do it. So again, for simplicity, well, for simplicity, I look at the toy model and just for beta equals 0. So maybe I should give a title. Or maybe not, I will just, okay. So let's do it, energy method. I'll just do it for beta equals 0. And I take, after scaling, I can assume that the other coefficients are equal to 1. Okay, so my system reads as follows. So I'm sorry, it's very elementary what I said today, but I think it's important to start with this elementary example, because it turns out that the general situation works the same, more or less. Okay, so I have this very simple system, and I would like to, well, to get a part of the table just by doing very simple, without computing the solution at all, just by basic energy argument. So the basic energy balance is this one. So it's very easy. I mean, all my computations are formal, but well, it's in our system, so it's not a big deal. So you take the L2 scalar product of the first equation with Q, and then you integrate. Of the second with U, and then you integrate. You sum, you integrate by parts. After integration by parts, you see that these two terms will cancel out. And you end up with this very simple relation. So the sum of the L2 norms of Q and U square plus U L2 square equals 0. Is it good or not? Well, it's not satisfactory because compared to the analysis that I did, we lost some information. Okay, you have some dissipation on U. You can look, you see it directly, but you have nothing on Q. And according to the table, so what should happen? So according to the table, you should be able to get a psi square, because you see that on this table, somehow you don't have really distinction between Q and U. At least for high frequencies, it looks that everything behaves in the same way. Okay, so for high frequencies, beta equals 0, you should have a kind of exponential decay for the two unknowns. And for low frequency, you should be able to get a psi square. So what would correspond to that, on this inequality, would be to have in high frequencies, you expect to have also Q, but maybe with a factor 1/2. And for low frequencies, you expect to have psi square. Psi square will correspond to the, is exactly what you would get for the heat equation. So it would correspond to the gradient of U and gradient of Q. Okay, and you don't have it. So is there a way to get it just by energy estimate? Well, as this system is very simple, you can do it just by guessing. So what kind of quantity you can play with this equation, but I prefer to go to the Fourier at the Fourier level. So let me rewrite the system in the Fourier space. Okay, so the only bad thing that now it's complex valued, but apart from that, it's not difficult. And so what I will do a computation which is much more precise, because you see that this inequality is nice, but it's global. It doesn't distinguish between low and high frequencies. I would like to have something similar, but for each frequency. So what corresponds to this one, to the basic energy balance, just to say that for all, so if you compute Q, so in fact, it's partial derivative now. If you compute Q and U at psi, my notation maybe are not very good, okay? So you want to compute this, so it corresponds to multiply by the conjugate of Q hat here, by the conjugate of U hat here, to sum and to take the real part, and what you get is this. Okay, I omit the variables T and psi. Okay. And so it's a point-wise estimate in the sense that it's also for every frequency at every time. Okay, so this one corresponds to this one. Okay, just integrate and use Fourier-Plancherel theorem. So now I would like to have something that involves Q. So you see that something that can be done is to multiply the first equation. So if you multiply the first equation by I psi, and then take and then multiply by U hat R. So okay, what happens? So what I want to compute is this: the time derivative of I psi Q hat U hat bar. Okay, so from the first equation, what you get is minus psi square U modulus of U hat. And what is good is the second equation. So you take the bar here, and you will get a plus psi square. Maybe, yeah, a plus psi square Q. So you see it's nice because now you have a psi square and a Q square. And then you have a last term, which is this one. So maybe something of this kind. So I multiply by, no, maybe I shouldn't have, no, sorry, let me just multiply for the moment, better to multiply just by this. So in that case, the first one will give plus I psi U hat square. And for the second one, I will have, so this one has to be multiplied by Q, but I have to take bar of that. So I will have minus I psi Q square. And finally, plus Q U hat. Okay? And so now what I'm going to do, I'm going to combine this one and this one to get something nice here. Something nice, I mean, I would like to have something which is positive, and that corresponds to what I expect on the table. So clearly, it looks to be complicated to have the same. You will not be able to have a nice identity for all frequencies at the same time. So I will first assume that for psi smaller than 1, so I have two identities, 1 and 2. So what I do, I take 1 and I multiply the second one by what? By I psi. So maybe I psi is a bit too much, because if I do that, and I sum that I will completely, this term will completely disappear. It's not what I want, so maybe it's too much. I divide by 2, for example. I mean, it's like engineering. It's not something, it's not so conceptual, but it works. Okay, and as you want in the end to have something real, it's better to take the real part of that. Okay, and so what you get after computation is this relation. So far it's still an equality. So it's better that I write exactly what you get, that I do not do any mistake. I would like a white one. So where is it? So it's here. So what you get is this relation. So Q hat U hat square plus the real part of I psi q u. Okay, so this is my first term. Plus 1 minus psi square 2 u square plus psi square divided by q, 2q. And then you have, you still have this term that I shouldn't forget, which is plus so it would be arterial of I psi divided by 2 q u hat equals 0. So I have to erase this. Okay, so let me call this L square of T xi. So what you may prove, as you have psi is smaller than 1, so you are sure that this coefficient is at least 1/2. And this one is psi square over 2. So you have to find a way to eliminate this one as well. Okay, but this one, it's not too difficult to see that this term is dominated by the over 2 terms. Okay, you play with Young inequality, and then you can kill this term by the over 2 terms. So what happens is that this term may be bounded by from below by, for example, maybe it's not exactly the right coefficient, but something like that. Okay. So what happens finally? So for psi smaller than 1, I need a white chalk somewhere. No, it's not white. Okay, you end up with this inequality for psi smaller than 1. You get 1/2 d of L square T psi plus psi square 4 is smaller than 0. And not only that, something that I forgot to say, but something which is clear, that xi is smaller than 1. This product may be by Young inequality. You may bound it by q square plus u square divided by 2, which means that this L square is actually equivalent to the q u square. Okay, and so once you have this inequality, you end up with some exponential estimate which is this one. So for psi smaller than 1. Okay, now if you do the same computation of the heat equation with what the dTu minus second derivative of u equals 0, it's exactly what you get. You get the psi square. Okay, the psi square is you have a heat equation. Okay, so what I get here corresponds to this lower part, at least to a part of it. What I was able to get is not, I was able to get coefficient 2, not this one. So I was able to track the worst diffusive effect. So you can play exactly the same game for high frequencies. So for psi greater than 1, so you see what you have to do. Instead of multiplying by I psi divided by 2, you will multiply by I divided by 2 psi. And you do exactly the same type of computation, and in the end, you get L tick psi. So you have to modify the definition of L accordingly. Okay, it will be not this one, but you will have to divide by psi. And what you get is, so everything will work almost the same, except that here, every time you have to keep the worst coefficient between the two. And for if psi is greater than 1, the worst coefficient is not psi squared over 2, but it's 1 over 2. Okay, so in the end, you will get this exponential decay estimate. Okay. So what next? So what next? You have to think that the goal is not just to solve this very simple system. You can do it explicitly. There is no need to prove something which is not so precise. But in the end, what I want to do is the same on some nonlinear system. So if I want to solve nonlinear system, I need a functional framework, estimate, and so on. So the question is, from these two relations, what kind of estimates you can get? So it looks that it's related to energy method, so I have to think about Sobolev spaces. So the question is, what are estimates in Sobolev spaces? So from this and this, it's very easy to see that if you start with some data in HS, then you will have a control in HS for all time. Okay, yeah, so this is completely clear. But can you have some gain of regularity by performing integration? So the answer is yes for low frequencies, because like for the heat equation, and for high frequencies, it's a dumped equation. So you have no gain of regularity, but you have decay. For example, you can expect to have L1 in time control solution. But something important is, since the behavior is not the same in low and high frequencies, you have to use different spaces. If you want to get optimal results, you need to use different spaces for low and high frequencies. There is also something which is maybe not so obvious here, but if you start with this relation, if you perform integration with respect to space and time, then use Fourier-Planchard theorem, it will be very easy to gain this psi to the square, okay, which corresponds to a gain of one derivative by performing L2 estimates. But can you get more? I mean, is it possible to do, so I want to advertise the functional framework, so I have to explain. For low frequencies, so what you get from this relation, let's call it number 3. Typically, you will get QUT HS square plus so gain of one derivative. Well, up to some constant maybe. Okay, but it's only for low frequencies, which means that here it's true only if I truncate the function. And for high frequencies, so you start with 4, and you have so you have this one, but no gain of regularity. The question now is, and maybe important if you want to solve nonlinear problems with a critical level of regularity, So here, in low frequency, we were able to gain one derivative. And here we were able to get L2 estimates. Is it possible to do better? Is it possible for the heat equation, if you go below L2, you can expect to gain more than one derivative, okay? And here you can also hope to get more, to get also L1 integrability. So it turns out that if you do it in Sobolev spaces, it's not exactly possible. I mean, somehow it's possible, but you don't end up with very, very nice spaces. You have to mix time and frequency. It's not so nice. So what I want to advertise now is the use of a class of Bezier spaces. So it's not a question of doing a whole theory of Bezier spaces. I just want so it will be a super fast presentation of Bezier spaces. And I will explain why they come up naturally in this problem and why it's better to use them instead of Sobolev spaces. Okay, so I don't know how familiar you are with Littlewood-Paley decomposition. You know all that? Or absolutely not. No? Should I? Well, okay. So we have to start. Well, there are several equivalent definitions of Bezier spaces. But the one that I need today is really the one with Littlewood-Paley decomposition, because I will use Littlewood-Paley decomposition to work on the PDEs. Okay? So what is Littlewood-Paley decomposition? So this is a formal decomposition. Okay, you take some function z equals. So I will use the homogeneous one, which means that I will sum on all integers, positive and negative. So I want to decompose a function z in some small pieces which are well localized in frequencies. So I have to explain what the definition of this space, of this operator. Okay. So I need some function chi. Oh, maybe it's better to do a picture. Okay, so I need the normalization is not so important, but let's put it anyway. Okay. So I start with the function chi, which is equal. So chi is a radial function. Which is value smooth, which is, let's say, equal to 1 from 0 to 3/4. And then is non-increasing and compactly supported. Okay. And from chi, I define function phi, which is equal to chi like this, for example. Okay, so my function phi is like this. So this is chi. And phi starts here. And it will go to 0 at 8/3. So this is a function phi. So now from the definition, it's obvious that, well, if you write the sum of all phi to minus j xi, and you do the summation on z, you have a telescopic series, and you get 0, except at one point, except at 0. You never see what happened at 0. Okay. So now what is the definition of delta j? So delta j maybe I should put it here. So delta J, it's a spectral localization operator in the annulus Cj, which is the set of psi. So now it's completely general. I am in any dimension, okay? So such that 3/4 to the j is smaller than psi, smaller than 8/3 to the j. Okay, so what is delta j? Sorry, delta j with a dot. Dot because it's homogeneous, so the usual rule that you put a dot. Okay, so delta j acts on time-pair distributions. In that way, if you take the Fourier transform, then it's the multiplication by the rescale function phi, which is obviously supported here. Okay, so this is the definition of the Littlewood-Paley truncation operator. And then this, yeah. Oh, yeah, sure. Otherwise, it's not interesting. Yeah, sure. Sorry. Yeah, so now, formally, you expect to have this, except that you have the problem that this equality is not true at zero. At zero, in fact, the left-hand side is zero. And because of that, you do not see polynomials. So this equality is true in the set of time-pair distribution modulo polynomials. Well, this is due to the fact that I used a so-called homogeneous decomposition where I sum in all frequencies. There is a version of that where you put all the low frequencies in just one term, and then you avoid the problem. But the spaces that I need are really this one, because, well, when you work with critical regularity, it's more, and you do rescaling, it's much more natural to use homogeneous spaces. Okay. So anyway, I will get rid of this problem because you can avoid the problem with polynomials if you assume that you consider only distributions or functions that go to zero at infinity. So a way to do that is to assume, for example, so you consider a subspace of S prime of distributions that tend to zero at infinity in the following sense. If you truncate by, so you use a spectral truncator operator, which is here, the chi, you rescale it, you apply to Z. Okay, so this corresponds to what I did here, but with chi instead of phi. And then you ask that it tends to zero. While in infinity, for example, it's not so important, when J tends to minus infinity. Okay, so obviously, this set doesn't contain any polynomial except zero, of course. Okay, because when if you apply this to a polynomial, it will tend to some derivative of Dirac mass. Sorry, no, it will tend to the polynomial itself. Okay. And therefore, this identity, Littlewood-Paley decomposition, which is here, it really holds in S prime H. Okay, I can give now the definition of Bezier spaces. I think I will stop with that. Sorry? This? No, it's a D. Ah, you don't, the definition of this operator? You want me to define this? Okay, so I will write it explicitly, it's better. It's the same as here, except that you take chi. So it means that, okay, you go to the Fourier space, you multiply by chi to the minus j, and then you take the inverse Fourier transform. Okay, so it's a localization operator in frequencies in a ball of size 2 to the j. So you want this to tend to 0 when j tends to minus infinity in L infinity. I mean, I could have skipped that. It's just a technical point, but it's nevertheless important because if you use this definition and study nonlinear equations, then you may have troubles. Typically, you may see a stupid thing that you can do. You say, okay, u equals u times 1. So I want to estimate u. I have a product law. I will say that the norm of u is bounded by the norm of u times the norm of 1. But in this framework, you don't see 1. So the norm of 1 will be 0. So you have to avoid this kind of jokes. The reason it's good to have this definition. So now I can define a Bezier space. Well, of general Bezier spaces, but don't worry, I will use only a particular class, Bezier spaces. So the Bezier spaces, so you take any S in R and any Lebesgue indices P and R. And then you define BSPR to be the set of tempered distributions in this space, S prime H, such that the following quantity that I am going to define is finite. So what is this? Well, let's call it a norm. Okay, so there are 3 indices that will have 3 different roles. So first, you look at delta J, U, delta J, say, C. Okay, so you localize in frequencies and you take the LP norm in RD. Then you multiply, so the S will play the role of regularity index. So you multiply by 2 to the JS. And finally, you do some summation according to the exponent which is here. So you do a summation with respect to J. And you do the summation on Z. Okay, so it looks ugly, but tomorrow we see that first, Sobolev spaces enter in this class, and second, the space that I'm going to use are almost Sobolev spaces. Just a small difference. But I decided to give the general definition because it doesn't cost more somehow. Okay, so stop here today. So you can, in any, there is a lazy definition that works in any domain, that you do it by restriction in the sense of distributions. Well, it's abstract definition that is not so useful. And now there are alternative definitions of Bezier spaces, but they don't, well, there is one that works for all indices. You can always interpolate from more classical spaces like Sobolev spaces. But if you want to get a Bezier space with LP, you have to interpolate from Sobolev spaces which are built on LP as well. There are some range of exponents where you can use finite differences. So this is a definition that you can use in domains, but you have to be careful because of the boundary. You can use that in domains in general, but you have to be very careful. In particular, you have to be very careful if you want to use a high index of regularity. Because if you have index S which is near 0, it's more or less, it's okay because you don't see borders. You can just extend your function by 0 outside the open set. And it's the same space. But if S start to be larger than 1 over P, you will start to see trace, and then bad things can happen. Sorry? Yeah, S is a smoothness. Yeah, you will see. In fact, tomorrow it will be complete. I will prove that BS22 is HS, and then the meaning of this will be completely clear. Okay, maybe today it's a bit mysterious, but I will need 15 more minutes to